Hello, this should be the last video of this chapter, I think part 5. I'll try to complete everything in this video. If it is, if I think it's going little too much, then maybe one more video. But yes, technically, it should be the last video. So in the last video, we discussed about two properties, atomic radius and ionization enthalpy. And remember, ionization enthalpy was the energy required to remove an electron from an isolated gaseous atom in its excited state. When you want to remove an electron, energy is required because you have to overcome the force of attraction. And we understood that the easier it is, low is the ionization enthalpy. Therefore, from left to right, because it's generally, how do you think blindly if you want to visualize? Left is metal and right is non-metal. It's easier, metals want to anyway lose electrons, so it's easier for me to take it, right? So they have a low ionization enthalpy, or in other words, it kind of decreases, it kind of increases across the period. And the reason is because here it is easy for me because they themselves are willing to give, whereas right side, non-metal, they have a tendency to gain electrons, so it's very difficult for me if I have to remove an electron. And in the case of the noble gases, it's even more difficult for me to remove because they are all stable. And in fact, in the case of helium, helium has the highest ionization enthalpy because it's very small and it is very stable. It's not that easy for me to remove it. Right? Yes. Okay. Now let us talk about the next thing, which is electron gain enthalpy. The third property, electron gain affinity or electron gain enthalpy. Okay, it is denoted as delta EGH, electron gain enthalpy. This is how we write. Alright, now this is the energy gain as the name suggests. In the case of ionization energy, we need to supply. So this is the energy gained, or we should not say gained always, in most of the cases. Okay, involved, we'll say gain in most of the cases. Energy gained when an electron is added to the isolated neutral gaseous atom. Say, okay, is added to the isolated neutral gaseous atom. Like for example, you have a neutral gaseous atom like this, you add an electron to it, it will be minus charge, correct? And then it will gain some energy. This energy is what we call as the electron gain enthalpy. Okay, and again this is denoted in kilojoules per mole, that is the unit of this. It now, unlike ionization enthalpy, is always going to be negative because, an ionization enthalpy was always positive because you had to supply energy to the system. Whereas electron gain enthalpy is always, I cannot say always, in most of the cases negative because it's releasing energy, correct? Releasing means energy is losing out. But in some cases, like in the case of noble gases, it can be positive also. I'll explain why in some time. Okay. Now, what it actually indicates you, it indicates the tendency to accept electron. If I say there is an element which is having a greater tendency to accept an electron, more energy it releases, correct? If you are happy to take some people, you will be very much happier in life. Imagine you are more willing to accept something than one of your friend. That means you are more happy about it because you are gaining what you want and you will be radiating a lot of happiness around you. And this is very similar. That means you are giving a lot of energy. Right? Yes. So greater, what it tells you, if the delta EGH value is greater, that it means that it is more reactive. More reactive, the element, reactivity of the element is greater. That is what it says. In case of ionization enthalpy, we say lower is greater because in terms of metals we say, but anyways, I will summarize this at the end. But for now, you can understand this. Now, if you talk about group 1, this table is given to you also. This is group 16, this is group 17, and this is group 18 or group 0. If you talk about hydrogen, lithium and everything in group 1, you can see that it is minus. You don't have to remember this. This is just for your information. So, it is kind of reducing. I will explain why. Now, let us go to group 16 like oxygen, sulfur, selenium and all that. you will see it is minus 141, minus 200, minus 195 and so on. You can just refer the textbook. Just see the values. I don't want you to remember anything. Group 17, that is fluorine, chlorine, bromine. It is minus 328, minus 349, minus 325 and so on. And if you talk about group 18, for helium it is plus 48, for neon it is plus 116 and so on. And look at the table in your textbook also. I cannot have a pattern. Look at that. It is increasing, decreasing. Increasing, decreasing. It's weird. Okay, so as such there is no trend. There is a lot of exception. But in general we can write some trend. Okay, now what are the factors with respect to this? Like you can see that. Now left to right I will just tell you here. In general, okay, you can see exceptions also like I mentioned. Because it is increasing here. Then it is becoming positive. So in general, when you talk about left to right, across a period, what happens? Atomic size, you know, is decreasing. Or the effect, because of the effective nuclear charge is increasing. And if the atomic size is reducing, if I put an electron, it is able to hold it better. Now, gain enthalpy talks about when an electron is added, what is the energy released. But adding is not just like you add it. It has to hold the electron and bind to it forever kind. Correct? So, in the case of fluorine, it is a very small size compared to hydrogen, oxygen. So, it can bind it better. Or in other words, if you're talking about this, the size is not so much. The thing is, if you're talking about metals here, they have a tendency to lose electrons. If you give them something, they will not appreciate it. That's why they will release less energy. Whereas, in the case of fluorine, now this negative sign is only indicating that it is releasing energy. In terms of the values, you will always look at the number, ignoring the sign. Alright. Now, hydrogen is less, oxygen is 140 and this is 328. That means fluorine is giving you more amount of energy. And the reason is because it is non-metal. If you take one electron, it would have attained octet stability and it is very happy to do it. Whereas oxygen requires two. So if you are giving one electron, it is little happy. Fluorine is the most happiest because it just needed one electron and just you are giving him the right thing. Correct? So atomic size is decreasing, whereas electron gain enthalpy will increase. It is just like ionization energy. Ionization enthalpy is also increasing. The reason, now people usually get confused. They think that, see, they are opposites, which is true. Ionization enthalpy means you have to remove one electron, so energy is required. And electron gain enthalpy means you'll have to add an electron, so energy is released. So they feel they are the opposite and the trends are also opposite. But it is not correct. What is the thing here is, logically think, from left to right, if you talk in terms of ionization energy, you need to supply energy, correct? Metals are in a position to lose electron. It's easier for me to lose an electron. So I require a little bit of energy. And that's why it is increasing. Because for non-metals, they are in a tendency to gain electron. If I am trying to remove, I need to supply more energy. That explains why this is higher. Now let's come to why Eg is higher, electron gain enthalpy is higher. Like I mentioned, these people do not want an electron. They are in a tendency to lose electron. Now if you are forcibly adding, they will not like it. So they will release only little bit of energy. Correct? If you force somebody against their wishes, then they will not be happy. Right? I can say more happy means you'll radiate more energy. Correct? So it is less here, and here fluorine wanted an electron badly and you're giving exactly an electron. It's very, very happy. So high Eg. And obviously the trend, if you go down the group, atomic size will increase because of the number of shells. Ionization energy was decreasing and electron gain is also decreasing. Why ionization energy? Here the size is greater. It's very easy for you to remove electron. Correct? So it's more here and it's less here. Let's talk in terms of electron gain energy. Here the size is small, here the size is big. If you are adding it, nucleus has to hold it. It's easier for the nucleus to hold if the size is lesser. So electron gain enthalpy is more. You can see it right here, but of course there are variations, but in general you can see. If you see, only for chlorine there is a variation, but in general if you go down the group, it actually reduces. This is a general trend. As such, it does not have any trend. There is a lot of exception, but generally the trend is very similar to that of the ionization energy. or it's opposite to the atomic radii. We will list down all the factors, but yes, this is the overall thing. Okay, now if they ask you factors affecting the electron gain enthalpy, you have the same very factors. First one is atomic size, which we have already covered, but let me list it under the factors influencing electron gain enthalpy. Okay, so under factors, you have first one is the atomic size or the atomic radius. And the second one is the nuclear charge, which both we have discussed. Correct? Yes. Now atomic size, if I have to just talk about atomic size, if the atomic size increases, then electron gain enthalpy, if the size is bigger, it's difficult for you to hold, so it kind of reduces. Right? So they are inversely proportional, we can see. In fact, both ionization energy and electron gain energy is inversely proportional to the atomic size. Okay, and how about nuclear charge? We are talking about effective nuclear charge. If that is increasing, atomic radius is decreasing because of the shrinkage, and only if you are talking about nuclear charge, I cannot say combined effect is what we decide, but anyways, exclusively in nuclear charge, the nucleus is shrinking. If the nucleus is shrinking, smaller the size, better is the energy release. Alright, so this is what it is. Now, like I told you, the trend is already discussed. If across the period what happens, only electron gain enthalpy across the period, it will increase. Logically, you can think from metal to non-metal. Non-metal would want an electron, so that's the reason it increased. But if you have to explain it, you will say atomic size decreases across a period because of the effective nuclear charge increase. Force of attraction is greater. Therefore, the electrons it's easier to hold, and they give out more energy, and it decreases down the group. I told you, whatever increases here will decrease here. Opposite is the trend. The reason is because as you go down the group, extra shell is added, the atomic size is more. If the atomic size is more, if you are adding an electron, it's difficult for the nucleus to hold that newly added electron. Alright, so this is the second. And the third factor here is the electronic configuration. That also kind of affects the electron gain enthalpy. Atoms with outermost configuration, either this or Ns2 Np3, that is half filled, or Ns2 Np6, that is completely filled, they will have low electron gain enthalpy. And the reason is because they are already stable. They do not want. If you do not want anything and you're supplying, you're not much happy about it. Like, I don't wanted this, but you're still gifting me. I don't want that. Okay, so you're not very happy about it. Correct? But in the same thing, if you're talking about ionization energy, it was very high. Remember, ionization energy was high. I'm writing it because it becomes easier for you. Alright? Think about it. Ionization energy is the energy required to remove. If it is stable, it is difficult for me. Right? So that's why high ionization energy. Okay, yes. How about for the rare gases? Noble gases, it is positive, or we say it is zero also. The reason is because, what is the meaning of that? If you want to put an extra electron, they already have filled thing. Now, if you are going to put an electron, now don't think in terms of this here. What I meant is, if you want to put an electron forcibly, then they will have to occupy the next shell. And that's why it is very difficult, because they already have filled configuration. The newly added electron will have to go to the next shell, unlike all others. Correct? And that's the reason they are noble. They have positive, we say. They do not give out energy. In fact, we have to give energy if you want to forcibly accept it. Okay, that's the reason it is positive. And if you talk about in general halogens, these are not factors, by the way, these are just points. Okay, so I will just write this. Yeah, if you talk about halogens, they have a high electron gain enthalpy, because the reason also they might ask you why it is very high. The reason is because in the case of halogens, they only require one electron, and you are if you give one electron, they will attain stability. You are just providing what they want. That's the reason it's very, very high. They release more amount of energy. Right? Yes. Now again, if you're talking only about halogen, you have fluorine, chlorine, bromine and iodine. Correct? So it decreases. Now if you're talking from here, it is decreasing, just like the trend, because Smaller it is, it's easier. But only in the case of fluorine, it is, you have seen the value also. Let me write it. It is minus 328, minus 349, minus 325 and minus 295. You see that it is decreasing. Here there is increase, correct? The electron gain energy of H is greater, fluorine is lesser than chlorine. This is because of the relatively small size of 2p orbital in fluorine. Now in the case of fluorine, what happens is, let me write the configuration. It has 7 electrons here, and fluorine has also 7 electrons in the weightage. Now technically it should have been easier for the fluorine because it has got only 2 shells, and if you add it, it can hold it better than chlorine. And that is how it is the case, the decrease in trend is explaining in this case. Okay, why? Now forget about fluorine. Why chlorine has the highest among these three? That's because it can hold it better, because only 3 shells. Near it, it's able to hold it better. Now in the case of fluorine, though it is able to hold it better, because of its small size of the 2p orbital, there is repulsive forces. There is repulsion between the electrons because it's very, very closer, it's crowded. Now the nucleus is able to control. Now imagine a parent who is in just a very small room and he's trying to control 7 children. Now though because the children are very less, the parent might find it easier for them to control in terms of distance. But there are too many children. In a very small room, if you have to control, one is shouting, one is doing this, it's very difficult, right? Exactly the same reason. Alright, so this is about electron gain enthalpy. Yes. This is the third property, and the last property here will be the electronegativity. Very, very important, because we are going to deal with this a lot many times in chemistry. We even talk about electronegativity in organic chemistry, so in redox and everything else. So this is super duper important aspect. Electronegativity. We are not going to discuss electropositivity as such, because if you understand this, I think it's very obvious, but if you want, I will just mention at the end of the class. What the definition is very, very important. It is the ability of an atom in a molecule. Now this word, look at that. Till now we were only talking about an atom or an ion. This is the first property which is talking about something in a molecule. Alright, so the ability of an atom in a molecule to attract the bonded or the shared pair of electrons to itself, towards itself. Alright, what is the meaning of this? I'll just give you an example. What is the meaning of this? Now this is very evident that it is just in the case of, this is in, what is it? Okay, it's talking about a molecule, right? So ability of an atom in a molecule. Now if the definition looks like, what does, we have just done electron gain enthalpy and electronegativity. Both, what do they tell you? They talk about measures of electron attracting power. Just let us talk about gain enthalpy a bit, which I just explained a few minutes ago. Electron gain enthalpy means if you are giving an electron, how much energy it is radiating, and more the energy it radiates, that means more it loves electrons. Like in the case of fluorine, if you go across the second period, fluorine is having a very high electron gain enthalpy because it wanted one electron and it is giving energy. This is also talking about the same thing, but what is the difference? This electronegativity, if you are saying, that refers to an atom in a molecule, whereas electron affinity talks about isolated atom. Remember the definition? Gaseous isolated atom. Right. Now, I'll just give an example. What it means is, now if you are having, now it talks about the bonded pair. So think about it. If you are having 2 oxygen, you know how a bond is formed, right? 2 pairs of electrons are shared. I'm not talking about others. So it's a double bond. And because both of them are same, so the bonded pair will be at the center. But if you talk about HCl, okay, you have this. Chlorine had 7 electrons, correct? 1 it will share, and hydrogen had 1 electron which it will share. Okay, so there is a bond here. Now chlorine has shared one electron and hydrogen also has shared one electron, and they decided that we can access each other's electrons. But chlorine, because it loves electron more, because if you give one electron, it is in the verge of completing its octet, right? So it will kind of, instead of keeping it in the center, it will pull towards itself. So that is what is electronegativity. This is talking about a molecule. Look at that. In a molecule, when compounds are formed, if the element has a greater tendency to shift that electron cloud towards itself, then we say it is more electronegative. So electron, both of them are talking about electron attracting power, but electron gain enthalpy, this is affinity I mentioned, it's the same, e.g. whatever. It talks about an isolated atom. If there is an isolated atom, how much it loves electron or it doesn't like an electron. And electronegativity talks about something which is happening in a molecule. Alright, if the molecules are same, that doesn't make, this definition doesn't make, but in this case we understand, like in the case of this thing. And electronegativity, I'll give you a simple thing, you have to remember this, okay, because it's very very important. Okay, so what is this is super duper important, alright. Fluorine is the most electronegative. Fluorine is the most electronegative element. I'll tell you why also. After that, in the entire periodic table, okay, after that it is oxygen, nitrogen, chlorine, somewhere carbon, somewhere hydrogen, and after that it is metals. This is very very important. Alright, so let us understand the trend, what happens if you go across the period and what happens if you go down the group. It's very obvious across the period. I mean, logically think it's becoming metal, and here are non-metals. Non-metals will pull it towards itself. Metals will push it. So naturally, electronegativity will increase. Whereas down the group, it is talking about size here, because down the group, if I see, now here also let us talk. The electronegativity increases just like other things. Now look at that. If I have to summarize, maybe I'll write it here. First, let's talk about electronegativity. Why it increases, don't write like metals to non-metal. In general, it increases. The reason is because the effective nuclear charge is becoming more. The nucleus is becoming little bit smaller and smaller and smaller. If they become smaller, it's very easy to pull the shared pair towards itself. Correct? Because the nucleus is becoming more stronger, the size is smaller, it's easy for me to pull it. And the more I pull it, more is the electronegativity. Now when you talk about this, electronegativity will decrease because again of the same thing. Down the group, the size is becoming more. Correct? Size is becoming more. So fluorine can pull it better because of its smaller size, whereas chlorine and all, they require large size. In fact, the electronegativity of fluorine is 4. The electronegativity doesn't have any units because it talks about relative scale, right? We have a scale which is called as Pauling scale. So in the Pauling scale, fluorine is the highest, 4. Chlorine is next, okay. Bromine is like, let me write it for this only, bromine and iodine. Fluorine is 4. No units. Units are there for ionization enthalpy and electron gain enthalpy because they are energy related, kilojoules per mole. But here there is nothing. This is 3, this is 2.8, this is 2.5. You see it is reducing, and I told you the reason why. Right? Yes. Now, let me just summarize everything put together. Okay. If you are talking about atomic size, it decreases because of the effective nuclear charge, ionization enthalpy, electron affinity or gain energy, electronegativity will increase. All the three have their opposite to atomic size. The reason is only because of size. The smaller the size, in terms of ionization energy, if it is smaller, it is difficult to remove, correct? So that's the reason it increases. If we are talking about electron gain, smaller it is, it's easier for them to hold it better, so it is more. I mean, it will give out more energy. And in terms of electronegativity, smaller the size, it can easily pull, so it is highly electronegative. And opposite is the case here. Atomic size will increase, so electron ionization energy, electron gain enthalpy, and electronegativity will decrease. Very, very simple. Alright, so atomic, everything, all the three are same and they're opposite to atomic size. So if you technically remember atomic size, it will be very easy for you to remember all of this. Alright, now one thing I will just write everything in one piece is like, if you're talking about metals, you know they have low ionization enthalpy because it is left to right. Everything is low for metals. Okay, low electronegativity because they are more electropositive. I mean, what is electronegativity? Tendency to pull the shared pair of electrons towards itself in a molecule. Metals will never form a covalent bond. Think about it. They are always ionic. So very low electronegativity. And low electron gain enthalpy also because they are in a verge to release an electron and you are unnecessarily giving it. So that's the reason. Whereas non-metals will have everything high. Correct? High, high and high. By high ionization energy because you cannot separate it because they are in a need for gaining an electron and you are trying to remove it. High. They want to gain an electron and you are exactly giving one electron, so it will release more energy. That's why high. And they are hungrier for electrons, so they will pull it towards itself. So they are very, very high. Now in terms of reactivity, I'll tell you, lower the ionization energy, you say it's more reactive for metals. For non-metals, higher the electron gain enthalpy, we say more reactive it is. Okay, that's the reason first group elements which have the lowest ionization energy when you talk about metals. In the first group, everything is a metal, right? So lower ionization energy means they're highly reactive. You can recollect the reactivity series also. And in the case of non-metals, the 17th group. Why? Because they have the highest ionization, electron gain enthalpy. Alright, we only talk like this. For metals, we deal with ionization energy. Lower it is, it's more reactive. When we talk about non-metals, electron ionization energy doesn't make any sense because non-metals have a tendency to gain electron. So this makes more sense, and higher it is, more reactive it is. Okay, now fluorine has the most electronegativity. Cesium is lowest. So cesium is the lowest electronegativity. It is about 0.7. That means it's highest electropositive. It is in a tendency to give away electron. Electronegativity of hydrogen, if you see, it is 2.1 and it is exactly the dividing line between metals and non-metals. So that means hydrogen electronegativity is 2.1. Metals will have electronegativity which is less than 2 and non-metals will always have electronegativity greater than 2. And inert gases, if you see, they will never form molecules. So there is no concept of pulling it. So they have zero electronegativity. Now, why are we even learning this electronegativity thing? It's useful when you write proper formulae. Like you write sodium chloride. Why don't we write this? Have you ever wondered? Because the rule says that more electropositive should be written first. Now HCl also. Both are non-metals, but fluorine, remember chlorine comes here. Hydrogen is 2.1, chlorine is 3. So it's more electronegative. Whichever is more electronegative should be written at the end. Alright, so that's why it becomes very, very important. Now remember, when we speak about electronegativity, it has a trend, whereas electron affinity does not have a regular trend. Summary also I have mentioned here. Alright, so yes. Now that we have done with all the properties, we just have 3 topics to be completed and we are done with this chapter. Let me try to finish that this thing also. I think another 10-15 minutes. It's fine if this video takes a little long because they are just small topics and we can easily finish them here. Yes, the first thing is about valency. We can also call it as oxidation state, but it's slightly different. For now, you can remember, we will talk more about it in redox chapter. So wait, what is valency? You already know this. It's the combining capacity of an element. What is the meaning of this? Let me take H2O. We say the valency of hydrogen is 1 and oxygen is 2. We crisscross the valency, right? What is the meaning of this? Why hydrogen's valency is 1? Let me write it. For hydrogen it is 1 plus, and oxygen it is 2 minus. This is what you know already, correct? But how do we relate it to combining capacity? Hydrogen is only combining with one oxygen atom, therefore its valency is 1. Whereas an oxygen atom is combining with 2 hydrogen, that's why its valence is 2 minus. Minus and plus only talks about whether it's in a tendency to lose or gain electron. Correct? Now it depends. What does it depend on? This valency depends on the number of valence electrons. Correct? If you are talking about S block elements, that is group 1 and 2, they have, let us write the valence electron from 1 to 2 and from 13 to 18. Okay, let me write it neatly. Maybe yes. 13, 14, 15, 16, 17, 18. What is valence electron and valency? Valence electron, it is increasing. You can see that. Because in groups it is like this. So we say that left to right the valence electron increases. But what about valency? It has one electron, it kind of loses it, so it is 1 plus. 2 electron, it wants to lose that, because if it loses 2 electron, it can attain octet. 3 electron also it can lose. And here, once it is 5, it will try to gain 3 electron, because losing 5 is costly affair. Okay, it will gain 2 electrons, it will gain 1 electron, it will not gain anything. This is what it is. So we say the valency kind of initially increases and then decreases. But also remember, up to here it is fine. Technically, though it is 3 minus, it can also be 5 in some cases, which we will talk about why in the coming chapters. Okay, so it is 2 6 or it is 1 7 or it is 0 8. This is how it is. Now why, what is this? Like I said, it is a little shocking because till now we have always understood it this way, but we will understand it why in the next classes. Alright, next when you talk about redox and chemical bonding, you'll understand it better. Now if you are talking about D block, that is transition elements and inner transition elements, they exhibit variable valency. Okay, why also we will understand that later on. When we study D block and F block, you'll understand. But it is something to do with the hybridization concept, which you will study in bonding. Little bit you will understand when you do bonding, but you will understand it more next year. Alright. The common valencies are 2 and 3, like in the case of iron and all that you can see. Right. Now valence of elements, you can say it initially increases and then decreases to 0. Within a group, if you are talking within a group, the valency and the valence electron will be the same. Meaning, I am not saying the valency is same and valence electron is also same. And 18th group will have 0 valency because they are inert. Alright, so that's about valency. Nothing much. This is exactly the same thing which I explained in last year, but this topic was deleted. But anyways. Alright, next is about the anomalous property. This is very important. They can ask you for 1 marker. Anomalous properties of second period. The second period elements, they are a little weird. They have some exceptional properties. Alright. Now, what is the second period? I am talking about the second period. What it starts with lithium. You have beryllium and then you have boron, carbon, nitrogen, oxygen, fluorine and neon. Let me also, only the second period is different, but let me just write it. This is sodium, this is magnesium, this is aluminium, this is silicon. Okay. Now the exceptional property is this. Some different kind, they vary. The first group of each group, the first element of each group, that means the second period elements, right? So if you are talking about each group, and if I say the first element of each group, what is the meaning of this? First element of each group. It means all the second period elements, correct? If you are talking about lithium, beryllium, and that is from boron to fluorine, they differ in many aspects from the other elements of their respective group. See, technically lithium, sodium, everything should behave same. But the second period elements, they behave a little different. Now, below sodium you have potassium and all that. They all are similar. But lithium is a little different. Beryllium is a little different from other members of its group. Okay, and they are more similar to its diagonal element like this. See, technically lithium should have behaved like sodium, but only in the case of lithium it will behave like a magnesium. That is what we say diagonal property also. This is also called as diagonal relationship. Lithium, instead of behaving like sodium, will behave more as magnesium. I'll tell you the reason why also. Beryllium behaves more like aluminium. Okay, instead of behaving like magnesium. Now, let us see. Okay, the reason is, if you think about beryllium, now all the second group and first group are metals except for hydrogen, and metals should form a ionic bond, whereas beryllium is trying to form a covalent bond. We'll understand the reason why also. That's the difference. Alright, now each element will actually try to resemble an element of the subsequent group in the next higher period, like diagonal relationship. That's what I mentioned. Now let us understand the reason why this anomalous behavior is there in the case of second period element. What is the summary? Lithium, or each thing in the first element of each group, or all the elements of the second period, they are very different from other members of their group, and they are more similar to like the member of the in the diagonal member in the next period. All right. The reason, the one of the property is like beryllium is more covalent. Technically, it should be ionic, and lithium behaves like magnesium. Now, let us try to understand the reason. One is, you have to please remember all this. One is the small size. All the second period elements have only two shells. Two orbits. Correct? Two shells. Electron will be in the 1s, 2s, and 2p. Correct? Only is very smaller size. They have a large charge to size ratio. What is the meaning of this? Charge to radius ratio. It's obvious, right? See, charge by radius. Radius is very, very small because there are only two shells. So, obviously the ratio will be high. Right? So, they have a very large charge to radius ratio and high electronegativity for the first elements in each group. If you are talking in terms of group wise, electronegativity is very, very high compared to other groups, right? I'm not talking about this, I'm talking about electronegativity with respect to each groups. Okay, each group. Like lithium is more electronegative as compared to it because it's smaller size, it can acceptance is better there. Correct? Now, furthermore, the first element has 4 valence orbitals. Look at that. All these elements have 4 valence orbitals. What is the meaning of that? We are talking about orbitals, right? So, you have 1s, which is the innermost. This is gone. This is 2s and next is 2p. This is the valence shell for all the elements in the second period. How many orbitals will be there? There are 2s orbitals and there are, 1s, meaning in the s orbital. In the s subshell, you have 1s orbital, and in the p subshell, you have 3 p orbitals. So, totally there are 4 valence orbitals. Correct? And these 4 orbitals can bond, can mix. Okay, you will learn this exactly in the next chapter. Whereas, if you go to the third period, look at that, their valence shell is 3s2, 3p and 3d. Right, third period. Of course, 4 is there, but I'm talking about the valence shell here. 1 orbital here, 3 here and 5 here. They have totally 8 orbitals available for bonding. So, they can perform better. Right. Maximum covalency of first member of each group is 4. That means 4 it can bond. So, it will form maximum 4 bonds because it only has 4 shells. Whereas this can expand their valence shell to accommodate more than 4 pairs, and that's the reason why they are behaving, because there is a limitation. Down onwards they can expand because they are getting more and more space. Okay, now this exact thing, like I mentioned, it's little unclear at this stage because you'll have to know about what is bonding and all that, which you will study in the next chapter. Alright, so for now only the reasons are important why the second period elements, or in other words the first member of each group, why are they different, and there is a diagonal relationship. The reason is because of its small size, there is more of crowding, there is a large charge to radius ratio, electronegativity of each group is very, very high, first element of each group, and they will have only 4 orbitals available for bonding, whereas the third period onwards they have more orbitals available for bonding. So, they can expand their valence shell to accommodate more than 4 pairs of valence electrons. which you will, this part like I mentioned, it will be more clearer when you study about chemical bonding. Alright, so that is about the anomalous properties, and the last topic here will be about periodic trends and chemical reactivity. Okay, now first let us talk about reducing and oxidizing nature. Okay, now oxidizing, what is oxidizing nature? Oxidation, let me write first, then we will talk about oxidizing nature. Oxidation, remember, LEO. If somebody wants to lose electron, they undergo oxidation, and reduction is when there is gain of electrons. Okay, when they gain electrons, they undergo reduction. So that means when you are losing electron, you are becoming a reducing agent, and when you are gaining electrons, you are becoming an oxidizing agent, or you have more oxidizing powers. Correct? So oxidizing nature will, this is the oxidizing nature, because you are helping others to oxidize. Oxidizing nature is talking about gaining electrons, and reducing nature talks about electron releasing capabilities. Which means if you talk about metals, they are in a tendency to lose electron. That means they are very good reducing agents. Correct? And non-metals are very strong oxidizing agents. Okay, and lastly, the second part is about the nature of oxides form. So if I have to talk about this, like left to right, you can now understand metals are good, the reducing agent is decreasing kind of, and oxidizing power is increasing. But they will not ask you, only remember this one. Now metals will form what kind of oxide? You know this. They will either form basic or amphoteric in the case of aluminium, zinc, tin, lead and all that. You know this. Correct? And non-metals, they either form acidic or neutral oxide. Neutral oxide is water. Acidic is carbon dioxide, sulfur dioxide. Metals, you know. So, and basic oxides, what will happen? They dissolve in water and they form base. Whereas acidic oxide, they dissolve in water to form acids, like carbonic acid, sulfuric acid and all of that. Correct? Yes. I think that's done. Please go through the summary once after watching this video. Let us do some quick questions which are there in the examples, so that you will get a feel of it. Okay, very, very small questions, and then you can do more questions from the exercise. Okay. Which of the following will have the most negative electron gain enthalpy? This is example 3.7. Okay. Example. Which of the following have the most negative? Okay. The question is most negative electron gain enthalpy, and which is least negative? Most and least negative. Okay. And you have to explain. Phosphorus, sulfur, chlorine and fluorine. See, the best thing is you have to identify whether it is across the period or down the group. That is the first thing. Now, in general, across the period, electron gain enthalpy generally increases, correct? And down the group, electron gain enthalpy decreases. This is what we know. Correct? That is, now we are talking about most electronegative, and it is becoming most electronegative if you go across the period. Correct? Now, let us try to understand which is, in this case, which is the most negative is chlorine, obviously, because now how are they positioned? Let us understand. Fluorine is here, chlorine is here, whereas phosphorus is here and sulfur is here, if you see. Correct? Now, obviously, now if you are talking about this part first, you see chlorine is the most electronegative, most electron gain enthalpy, correct? Because it increases, Eg is more. And if you go down the group, there's an exception. Remember, I told you fluorine is lesser because of the repulsion. So chlorine is more. Least is phosphorus, obvious. So this is the least. Okay, so this is one question. Next, yes, this is example 3.8. Predict the formulas of compound which will be formed by the pairs of elements silicon and bromine, okay, and aluminium and sulfur. What could be the formula? Now, silicon is in the 14th group, so it will have a valency of 4 and bromine is 1. So the possible formula will be SiB4. Okay, and aluminium and sulfur. Aluminium has 3, and because it's in the 13th period, and sulfur will have a valency of 2, so it's Al2S3. Okay, so this is the thing, aluminium sulfide. Yes, there are other compounds also which is there in your book. You can just check out that. Yeah, oxidation state and covalency is given, but let us not talk about covalency because you don't know that yet, right? So let's not talk about that. Yeah, I think this is enough. Alright, so you can do more questions from the textbook. Any other doubts, you can always get back to me. Yes, this is the last chapter and this completes the chapter. Yes. Alright, bye bye.